Okay, everyone, it's 9 o'clock, and I'd like to welcome you all to our latest webinar in the series. Today we're going to talk about some drainage stuff. Mr. Ron Mader and Mr. Doug Gesso from our drainage branch have agreed to show off a few things. Mader's going to talk about high 8 today, and then he'll pass it off to Dougie Fresh, and he's going to talk about some ditch analysis. If I can get this to move. There we go. The upcoming schedule. So far we've got a couple of them scheduled. February 18th, Troy is going to talk about inroad site visibility. That's been a popular one on our poll surveys at the end. And then on March 4th, Patrick's going to cover intersection radius modeling. I've got a poll question for you guys. We'll go ahead and kick us off. Actually, we got a lot of polls today, so let's go ahead and jump into it so we don't eat up too much of Mader's time. Okay, I'm going to go ahead and close this one and just to kind of look at what's going on. About almost a 50-50 split. We appreciate everybody who has been attending these before. Hopefully it's valuable. And if this is your first time, then where have you been? For anybody who's new, just a few things. We do give PDHs for this. We'll email out certificates for everyone that signed up. You have to be signed up to get the certificate from us. If you register and watch in a group, you can keep the sign-in sheet in your office. And when we give you the person that signed up gets the certificate, you can pass that out to others if you want, or create your own certificate for them to get PDHs. So it is possible to watch this as a group. And at the end, you'll get a survey that will have some questions. Very important to get your feedback on that. And definitely the last question should ask for some other topics that you might want to see, and hopefully we'll get some good information from you guys. Before Mader takes over, got a couple of more poll questions for you if you'd humor us, just to see what kind of software you guys are using. So if you would, please respond. This one should be an interesting spread. Okay, go ahead and close that out and share that. Hopefully you'll be able to see. We got an interesting spread here. About half the people on here are using the spreadsheets. Not much love for WMS, but that's probably not too shocking. And then one more, I promise, right now, and then we'll get into it. Okay, well, in that one, a lot of height users, which is good. We're going to cover some of that today. You may be bored, but maybe Mater can enlighten us. About 5% are like me. They're Katie did holdovers, don't want to let go. So that's good information. Appreciate that. Mater, are you ready to go?
I guess
I'm going to give you control.
Am I in control yet?
You should be.
Can y'all see my screen?
No, actually not. What is going on here? Let's see. Technical difficulties, please stand by.
I can click to start sharing. Is that what I should do?
Yes. There we go. Now we got you, brother.
All right.
Go forth and educate.
So this, I'm going a little bit too fast. Oh, there it goes. I wanted to get rid of that little screen. All right, good morning. Again, I'm Ron Mater, branch manager over drainage here in Frankfurt. And this is going to be an introductory session of our first time doing it. Hopefully, by doing this introduction, we can find out what it is everyone would like to have training on when it comes to drainage design, and whether we shoot too high or shoot too low on this, maybe the next time around we'll be able to target everyone in a better way. I'm going to introduce HY8 for culvert design, and now that I see so many are using HY8, I kind of wonder, we were told that this is just kind of introductory, maybe people wanting to use it, so we'll see how this goes, but this is very introductory, and I think maybe we might be shooting a little bit low on that. And then Doug is going to come after me, and he's going to talk about basic ditch design in the absence of high drain. Our focus today is going to be on practical application. We're not going to have any theory or equation derivation. I know that's a little disappointing, but that's my choice. Based on our real project is what we're going to use today. This is project up in District 9 that was built several years ago. We will look at some software, HY8, but there's going to be another software application we'll make use of for us to use HY8. And along the way, hopefully we could show how we're developing materials that go in the drainage folder. I had to assume that maybe the people who are interested in this are doing a lot of highway design, and then they have to come in and do a little drainage design at the very end, so maybe they don't develop this material that much. So like I said, it's more of an introductory lesson. Our audience, cabinet personnel, consultants who want some practical project-based design guidance. You need to have some understanding of the theory, and we're going to look at the final phase design for this. The project is in Fleming County. We're realigning that project quite a few years ago. Design and construction, as I said, was complete. We actually used this material. We did some training a few years ago across the state, and this comes from that material. That training will be available on our drainage website here in the next couple of days. For this training today, I extracted one pipe culvert, and we'll cover the design of that. And throughout the discussion of this design, we are going to try to highlight data that would go on the TC forms for documentation. And whenever you see the little red TC in parentheses, you will know that that data would go on the TC form, and I'll try to show that process along the way. The project location map is here. As you see, it's below Flemingsburg. And the first thing that we want to do before we do a drainage design is we need to get our IDF curves. You can see on the drainage manual in section 401, you can have instructions on how to do this. We go to the NOAA website if you haven't already done this. but we assume that you haven't or you don't do it very frequently. You go to the NOAA website, and what you need to have is for every project you need to have a lat and long, one lat and long. By having one lat and long, that means we are able to reproduce the exact same data no matter when we look at it. If we want to do another design for another pipe or whatever, that we have that one lat long and we can reproduce that data. From that, you'll go and you'll get a rainfall intensity chart. You'll also get a rainfall depth chart. I'm not sure if everyone does that. And then you can export that to a text file, and we'll use that in certain drainage applications. I thought it might be beneficial for those that haven't. Here is that site. The options are you can have your precipitation depth or your intensity. And so we picked intensity, your English units, and then partial duration is what we usually choose there. Here are your lat longs are entered here, and then you submit it. And after you submit it, you'll come and here's the data chart, and generally we just highlight this data, and you can copy it, like I say, to a text file. Okay. So that data is entered, and you'll save all this charts, and that would go in our drainage folder, both preliminary, advanced, and final. Now we extracted the culvert at station 378 plus 7950, and first thing we do when we look at designing a pipe is we need to get our quad maps. Aerial photographs are wonderful. Your topo sheets for your contours, any other characteristics that might be important for this, where there's sinkholes. You need your proposed roadway drawings and models. You also need to know how much traffic is using this highway. And again, at the bottom of every chart slide, we should have ones where you can know where to go in the drainage manual to get some of this information. Here's the plan sheet for this. The existing pipe or the existing culvert that we're replacing is a 1.5 by 3 foot box culvert, and we will first want to calculate what's the peak runoff discharge for this, both for the existing and the proposed conditions. And so we look at the existing culvert pipe upstream of the culvert, and also immediately downstream, because every once in a while it can be different, but we need to look at the downstream channel for the tailwater data. We also do the same thing for the proposed culvert. References for this are in our Drainage Manual, Chapter 400, also HDS2, Highway Hydrology. First thing we want to do is to get the watershed, and you'll get that, and for the existing and the proposed, because quite often they can be different. So the existing for this project, for this pipe, is 17.25 acres, and that goes on the TC form. Let's see if I can pull that form up. Here's the TC form, and just to begin to show you where data goes, here's the drainage areas entered here for existing, and down here for the proposed downstream channel. Okay, now we need to know what type of method do we use for determining our flow. And just a close-up of this, we go to this flow chart. Is there a flood insurance study? No. Does the project involve storage? No. Is the watershed less than 200 acres? Yes. We're going to use the rational method. We could maybe have to use a flood insurance study flows or NRCS unit hydrograph or a regional method, but in this situation we're using the rational equation. We now need to determine what's our design and check storms, and so you need to know what your ADT is, 6,500 for this. Again, here's the culvert, 6,500. We'd have a design storm of 25 and a check storm for 100. Now, what can you use to design? What software can you use to determine what the Qs are? Here are a few examples of what that can be for the rational method, the toolbox, our spreadsheet, storm and sanitary, and also WMS, which it looks like very few people use, and I can understand that. The hydraulic toolbox is what we're going to use to calculate our existing and proposed design storms. And the first thing we want to do is we want to come up with our C values. Let's see here. We're going to determine what our runoff coefficient is, and we'll end up looking at what the ground is like, what's covered the ground. Maybe you can see this, and I think I have another one here. But from looking at this, we get a weighted C value, and that will go into the hydraulic toolbox. Let me bring hydraulic toolbox over here. Here is the hydraulic toolbox, just in case I see that not everybody uses this. I've already entered the data in, but here is what you're after. You're after your CIA, or your weighted coefficient we determined for existing was 0.32. Your area for existing was 17.25. Now we don't know our intensity, and I know it's entered in here because this is already calculated, but we need to compute that. And so when you do that, you'll get this screen. Now the three things we need is our IDF data, which we just got from the NOAA website, and you'll enter that in here one at a time. It takes a little bit of time, but once you get it in, it'll work for your entire project. Then we need our time of concentration, and to do that, you'll need to have your sheet flow parameters, your shallow concentrated flow parameters, and your channel flow parameters, and they're entered in here. Now let me switch back to the spreadsheet just to cover this a little, to the PowerPoint. Again, we talk about it here. Your three parameters: your overland flow, your shallow concentrated flow, and your pipe flow, your channel pipe flow for existing and proposed. This shows that watershed, and here is the overland flow. Usually we look at the first 100 foot. You would have your upper elevation, your lower elevation, and your 100 foot, you would end up with a slope. And from that, from the aerial photograph, you'd also come up with an N value. So with those parameters entered into the hydraulic toolbox, you can get your first time of concentration for that length of flow. Your second part is your shallow concentrated flow. You'll need your length. You'll need your slope. Again, we have this elevation here. We're going to have an elevation there. So with the length, we have our slope. And then you also need an intercept coefficient. I might have an example. There's the intercept. That's a kind of a small example, but there you go. We ended up using 0.213 as a short grass pasture. Again, all this can be found in the HDS2 table, and I believe this might be in our drainage manual. And then the last part is the channel flow. Channel flow, we need to have our length. Again, we have our elevation differences. We also need to know a little bit about the channel geometry. I think in this example, we had like 6:1 side slopes for 600 feet. That was the estimate, with a 4-foot flat bottom. You also need to have a Manning's N for that. Anyway, from the hydraulic toolbox, let's see if I can get back to it. From the hydraulic toolbox, all these parameters are entered in, and you end up with an estimated time of concentration. And so after you have that estimated time of concentration, you are done. You come back and you will optimize, and after you optimize it, again, you'll see the result. You'll have the result for all your storms. You'll have it for the existing 25-year storm. 29.7 is your flow rate. Here's a spreadsheet that kind of shows that, but I kind of went through that. And here's the results we have from actually going to hydraulic toolbox. We have our existing and proposed flow rates, 29.7, 35.3, and they go onto our, here you get 29.7 here, 35.3, and the proposed goes down here in the TC. 61,100. All right, now we need to know the analysis for the existing culvert. We have done a survey. We know its length. We know its type. All these go into the TC 61,100. We know the Manning's N from looking at the field conditions. We also want to know what the head walls are like, square edge. We know the slope, and we need to know the load road elevation. With that information, we go to the drainage manual for doing culvert analysis, and the software that we can use to do this design is, there's several to pick from, and we're going to pick in this sheet recommends those. We really will receive just about anything that we can approve, but here's some examples. We're going to use HY8 for this. We need to enter the input data, the existing discharge from rational method. We need to enter in the tailwater data for channel shape and slope, which we get from our DTM or from a field survey. The existing roadway for overtopping calculations, and also the existing survey culvert data. Let me bring in, here is HY8. Again, most of you know how to use this, so feel a little bit funny just bringing this up, but since you know how to use it, here is the input data for the existing. The discharge data comes in here. We have a minimum flow. This is a 2-year storm design flow, and that's because I picked the minimum, design, and maximum. We have the design flow, the 25-year at 29.7, and the maximum flow of 35.3. The channel type, as I mentioned, was a triangular. Well, it's actually triangular. I thought it was a flat bottom, but it's a triangular channel. This is the tailwater data. So that's the reason. Is a triangular channel for existing. It's the side slope 6 to 1. The slope is 0.06. Our Manning's in was estimated to be 0.045, and our invert elevation for that tailwater is given there. The roadway data, usually on the first roadway, we're going to pick a constant roadway elevation. Usually we leave the first roadway station 0. Not sure why that's there. Crest length for this instance, we're going to use 100. Can't talk about all these values necessarily, but the crest elevation is 804.5. That would be if it's over top, what the elevation would be. Roadway surface is paved, and the width of this road is 21 foot. The culvert data, the existing is 1.5 by 3. It's a concrete box. You have several to pick from here. So we're going to pick a box, and here's the span and the rise entered in. Manning's in is selected for us. Its culvert type is a straight. There's the selections that you have, but ours is a straight. We have a straight edge head wall, and there's no depression here at the inlet. The site data input, our inlet station for this is 0, and here's the elevation for that. The outlet station is 41.4 units, and then the outlet elevation 797.3. We want to analyze the culvert at this point in time, and one of the things that we're trying to do in this situation is, which we'll see here in a second, is we have to decide what headwater we're going to design for. So let me go back to our PowerPoint. So we're going to analyze the results and compare the existing to the proposed. The headwater elevations will go into our TC form. The outlet velocity will also go in our TC form. That was the chart. That was the chart I just had up there. We're going to estimate a culvert size after we get this data. After that was the existing, and we're going to draw a section pipe here at the very end. I probably won't have time to get into that. The additional data is going to be collected for all this, and again, we're going to analyze the proposed first. Let me just go and skip past this. The headwater for the 25 and the 100 should be less than the existing, and because this is a replacement structure, we're going to look at for this situation, we're trying to design this so that this berm does not get overtopped. So elevation of 802.5 is what we want to keep our headwater below. And we also want to make sure that we don't have any damage to any property. So there's going to be other things that we're going to be looking at, but to keep this quick for this situation, we want to make sure our headwater is below 802.5. So we enter our input data for the proposed discharge from the rational method, our tailwater data, proposed roadway data. So let me go back to HY8. So let me close this. Now here's our proposed data. So here's the new design storms. We have our tailwater. We now have a more designed tailwater ditch there with the same invert elevation but different physical parameters. Here's the crest length and our new crest elevation and width. We are going to use a circular pipe, steel, and for example, this one we're going to use a 36-inch pipe, 3-foot diameter. And so the Manning's end selected, the head walls are selected, our site data is input here. We have looks like about a 117-foot length there, and then we're going to analyze that crossing. And for the 100-year storm, which I think the 100-year storm for this is 40.6, we see our headwater for this is 801.74. And again, this information will end up going into your TC 6100 form. Now, what we want to do, so it looks like, in a quick way, it looks like the 36-inch is going to work. What we might want to look at is see, well, what if we went back in with a 30-inch pipe? So we're going to look at a 30-inch pipe, and just in a quick way, 30-inch pipe for that flow. Well, I don't think I got it in there, so let's try it again. All right. What's that? Yeah, I did that, so... Oh, okay, I'm sorry. So anyway, I'm having trouble. What time is it here? Oh, okay, it's about time for me to quit. It turns out for the 30-inch pipe that the headwater data is below 802.5 for the 100-year storm, and because of that, we would not want to use that pipe for that. There's many different options we get here that you can use. Let me back up. So the 30-inch pipe proposed headwater was less than existing, but it failed to meet the ditch berm elevation. The 36-inch pipe is what we're going to go with because the headwater is less than the 802.5. The 36-inch pipe, we want to look at different alternates. We looked at the concrete and also the metal. Outlet velocity nearly matches for the CMP pipe, so we ended up choosing to go with that. There's several other things we need to look at, the velocities, and other issues need to be that might be of concern need to be noted on our 61100 form. These are refined. There's several other things which I need to pass this over to Doug here in a second, but we end up in our materials that we have that we will have on the internet. We'll talk about some of the other things that go into it. You need to check your cover, your fill height table, the type of head walls need to be added. Other things need to be put for your pipe section sheet. Anyway, that's a quick introduction to the HY8, and I want to pass this over to Doug.
Okay, well, they're changing out. I've got a couple more poll questions for you guys, so I'm going to launch this real quick. Let Doug get set up. Alright, I'm going to go ahead and close that one. And so it's a pretty good spread for what you guys are using to annotate vegetative lining. And I've got one more before we get into the last part of our presentation. Okay, I'm going to go ahead and close that. Again, pretty good spread, but most people are using the spreadsheet, as you can see here. So I appreciate your patience with those polls. I know there were quite a few. And I think, Doug, are you ready to go?
Yes, can you hear me?
Yes, I can hear you. I'm going to go ahead and turn this over to you. Just make sure you share your screen
Okay.
so we can see you.
Let's see. Okay, there we go.
Yep, now we got it.
All right.
Go ahead.
Welcome to the basic ditch design and analysis in the absence of high drain section, and hopefully we'll drill down and answer the question that is presented with this topic. Okay, because of the time limitations, it's just virtually impossible to cover everything, and that would be beneficial. But in order to address the topic, we're gonna drill down and focus on it. And that's about all I have to say about these. You can see what's what's missing. In regard to the references, of course, the KYTC drainage manual is one, and then HEC 15 is the other. And I did want to mention it was extremely beneficial to get a context for the topic based on the not only the current HEC 23 and HEC 15, but the past HEC 11 and HEC 15, as well as the documentation that comes with high drain. So that was tremendously beneficial. One of the perspectives on the title for basic ditch design rather than channels was I kind of wanted to focus on the fact that in the documentation it does provide general limitations for the depth of flow for HEC 15 at 5 foot, and also for Qs at 50 CFS and below. And this is referenced both in HEC 11 and in the KYTC drainage manual, a table for vegetation. You can see it, but it can be used beyond that, but it's cautionary that the end value approaches maybe are not required in those situations. What we've got here, we're going to kind of introduce some of the demo information. It'll come a little bit later, but this is the inlet flow ditch from the site plans at the inlet end, and then this is the actual post-construction results of the ditch. You can see it's performing fairly well. Looks like maybe it had a little help with the pond that we assumed would be not there. So that's what it looks like now. Some of the data that that we used was just straight off the plans. The slope of the ditch, and here it is. Here it's in a cut section at 15% slope, and then here at the pipe inlet, you can see it's a 2-foot flat bottom, and it's got a 1.5 foot of depth, and it was proposed with a Class 3 channel lining. Side slopes were somewhat uncertain, but we couldn't find it quickly in the plans, but it was utilized in hydrology. And another note was, of course, for a ditch, it's going to have a little bit different drainage area depending on where you're catching the flow in the ditch. This is the inlet ditch, so it had the flow from the drainage area of drainage area 14 minus a little bit. So the drainage area modeled is 7.6 acres. And let's see, it was adjusted. The other note would be that the design for ditches is 10-year design, and of course the check is 100-year. Now, we'll get into the details of this a little bit in the next slide. Recommended software, of course, Hydraulic Toolbox is one. This is the KYTC rational spreadsheet is the other. There's a new KYTC spreadsheet that's in development pending, being developed by Jason Littleton. And I had to throw this in at the end, the high drain high channel, and because it's recommended in the drainage manual, as well as you'll see in the next slide. The license fee, of course, watershed modeling system. It essentially refers back to Hydraulic Toolbox. And storm and sanitary can be done for rock line ditches. And there's a workaround where you could use it for grass. It would take a lot of manual iterations in addition to the database for the storm and sanitary channel configuration in the structures file. But anyway, that's a possibility, but it primarily can be used for rock. So we're going to drill down and focus here because this will, this will answer the topic of discussion. And you can see on the top are the three primary design aspects of ditches. You've got the design depth, the design lining, and then you've got the permissible shear. And the way the KYTC drainage manual is set up for grass and TRM, which is modeled as grass, it's a very prescriptive formulation in the manual where both require that for design depth relative roughness only is used, and for the design lining relative roughness only is used. In regard to riprap and gabions, these are essentially very permissive design criteria according to the manual, and it's represented here in the chart where both the depth and the design lining can be from the table, and on the other hand, where it is needful and beneficial, it can be the relative roughness. And when you take this route, you can use either option if it's beneficial. This option here normally would be it would be beneficial for steep slope design approaches. I should try to. In regard to the table values for design depth for the end value that's used, this is the DR505-1 table that it actually represents somewhat of a relative roughness values because it changes the end values based on rough depths, and as you can see, riprap, it has table values for the depths as well as other linings. In regard to the grass aspect of ditch design, one of the rationales, or I believe the reasonings for this prescriptive design is how greatly the end value can vary with the roughness, and it will affect the shear stress and the depth of the flow, and as a result, I think that's why it's required. Now, over on the design lining for the end value, because the the performance of the lining will depend on the shear stress. You want to get a little bit better estimate, a refined estimate on the depth to get a better estimate on the shear stress. So you don't have failure in your linings. That's the basis for this in grass, and again, either or in rock. Now in the permissible shear, the table value, I'll pull that over. It's from table 5054 in the drainage manual, and you can see the permissible shear values there for grass lining in pounds per square foot is 1, and all the other table value options. And so you can see that the table value only for vegetation is used by KYTC, and that's due to the fact that the effective soil stress approach used in HEC 15 is not currently recommended by our manual. So I guess in regard to the software to be used for each of these options, you can see that while there are several options for grass analysis, it needs to be noted that both the KYTC spreadsheet and the hydraulic toolbox, it utilizes the current HEC 15 method, which is not the method in the current drainage manual. High channel, it uses the current drainage manual method, and then there's a new KYTC spreadsheet that it will also be able to. It does use the current drainage manual method, and then there are other methods that can be used, such as manual iteration using the hydraulic radius and end charts to manually arrive in a simple fashion the shear stress. One other note in this section needs to be made is that the FHWA hydraulic toolbox, and of course I've already noted it, that when you do the analysis, you need to disregard whether it indicates it failed or not, because KYTC does not utilize the permissible shear stress criteria in that method. We utilize the table value, so you can still use the box, and I'll show you that in a little in the demo. In regard to TRM, this is it's somewhat of a problematic area currently. As I noted, the FHWA toolbox doesn't use the current drainage manual method, and also the KYTC spreadsheet doesn't extend to the higher shear stresses for grass. So the proposed new KYTC spreadsheet will do that analysis based on the current drainage manual method, and also noted high channel does it as well. Other methods would be available if it were manual iteration. So that kind of covers the grass and the TRM approach. In regard to rock, you can see that both high channel hydraulic toolbox and the KYTC spreadsheet is used in the relative roughness option, or both, either or, and then in the option for using just the table values. In this row would apply to less steep slopes, common mild slopes. This option would apply to steeper slope options where you get some benefit from adjustment of the Shields parameter in the model. Now, I should point out up here is any method that calculates the Manning's equation can be manually used to calculate the direct shear. So there is a simple approach that can be taken there. Now, one final note in regard to the riprap is that I've got some notes here on safety factors in various tools. Now, high channel, it utilizes the safety factor, but it's a user-defined safety factor. You can set it. Hydraulic toolbox and the KYTC spreadsheet both are prescriptive. They utilize the recommended HEC 15 safety factors. And I want to note that in that regard, the Kentucky the KYTC drainage manual is silent in the safety factor issue. It essentially leaves it unspoken. I think maybe one of the reasons is its steep slope design for rock is not specifically addressed. And that's where this safety factor issue comes into play. It is recommended in both the old version and the new version of HEC 15. In fact, those are identical in what they say in regard to use of safety factor adjustment of the shields parameter to arrive at a permissible shear in that method. And maybe as a side note to that is that in high channel, and it really needs to be pointed out, high channel documentation, it notes that the particle Reynolds value that triggers the maximum shields parameter for a higher permissible shear, it notes it at 10 to the 5th power, or 100,000 for the Reynolds number. Well, both the HEC 11 and both HEC 15 versions, the old and the new, are they use the statement of 2 times 10 to the 5th, and so it comes down to what it comes down to is a significant figures number. I think, and I think it's probably been misapplied in the past, that where users at 10 to the 5th would use that 100,000, anything above 100,000 would trigger the increased shields parameter. But technically, according to HEC 15, both old and new versions, the trigger is at 200,000 for the particle Reynolds number, and so below that it's a linear interpolation to get at the appropriate shields parameter. And so I just wanted to point that out, that that may be one aspect of what seems to, in some designers' perspective, being a change in the design approach or the allowables. Let's see. And finally, in regard to that, because of the recommendation for the use of the safety factor in these steep slope applications, and because of KYTC policy's silence in that regard, it ultimately rests with the design engineer's discretion on its use, and that's where it's left by our policy. Maybe as a final note on all of the software overview, if you'll note, high channel is in each one, and it is actually the only current software that does everything, and it does it very well. It's why I listed it in the previous slide, because it's still recommended in the drainage manual. There are workarounds to still utilizing it, and as I said, it does all of the functions that are required for KYTC design. If you don't use it, then you've got to look at all these multiple options, and that kind of is the basis for focusing and zeroing in on this slide, because it's needful to review this in order to know how do I analyze basic ditch design. Well, it's not a simple answer, and so it was necessary to address this here. And lastly, we'll go straight to the demo quickly here now, but I just wanted to throw up, this is the hydraulic radius to end chart that it references the relative roughness approach in our current drainage manual. This is a chart from the old manual with the same equations, and it can be used manually with the Manning's equation in another software approach to arrive at the appropriate end value for design. It kind of simplifies, the question if you wanted to, after going through all that complexity in the previous slide, it's really not that complex of an issue. It can be very simply done. So now we'll go to the demo, and for that, I'm just going to open up the KYTC spreadsheet. We want to enable the macro to work. So we've done that, and we've already input all the data that came from the hydrology. Of course, the channel segments were adjusted due to the inflow ditch having a 15% slope, and the other ditch was left had to be adjusted as well, and the drainage areas were reduced as we mentioned. But all the other data is the same. We've already loaded the NOAA data since Ron has showed that. We're not going to do that here, but it's simply it's included in the macro on this spreadsheet, and it's tremendously beneficial to have. You can see there's lots of aids for the designer to quick references to evaluate what the input is in the spreadsheet, and it's kudos to the developer of this, Richard Thomas. He did a super job at getting something that's before hydraulic toolbox came out that could do all of the riprap design that was necessary, and as well as vegetative. So so we've got the data input, and the NOAA data is already input. Now, what I would recommend, if you're especially, since this is we're looking at rock in this situation for this analysis, I would recommend using the option where you can see all the result data, and that way you can drill down and analyze what kind of results you're getting, see if it makes sense or not. So we've done all the input, and all you got to do to operate the macro is Control R. And this is just a warning that the Anderson roughness value, or the equation, is used instead of Bathurst and Blodgett to arrive at the appropriate end value. And it's due to, based on Richard's comments, was due to the some of the instability in the numerical output using Bathurst and Blodgett at very, very low depths. So, I suppose, let's see, first thing you might want to look at, well, we've got the 14 CFS for the 10-year storm design for this inflow ditch, and of course it has the end value. And it's interesting to note that relative roughness end values are being used even in the hydrology here. It's another advanced operation. As we go on down to the sizing for the riprap, you'll see a minimum D50 is indicated, and it's just over the class 2 lining, so that kicks us up to the recommended class 3 as noted here. The shear actual calculated shear stress 4.7, and for the 10-year. The permissible is calculated here at 10.6, and of course these values, they show the safety factor based on the adjustment of the Shields parameter as outlined in HEC 15, and that safety factor was 1.27. The Shields parameter adjustment from 0.047, that was adjusted all the way up to 0.103. Here's the particle Reynolds number, and you can see it's not quite up to 200,000, so it's not up to the 0.15 Shields parameter adjustment yet. This is a stability factor. It brings into play the side slope. Stability of the riprap is dealt in a particle fashion, and using vector drag and forces and shear forces from the water in slope, not only the slope of the ditch but the side slope, and it's it's kind of hairy getting into, but anyway, it aids in calculating the safety factor due to the side slope impacts, and then of course the area and the method that was used to arrive at the relative roughness N value. I think that about covers a primary overview of the results. I did want to show you one other thing here quickly. Use 2-to-2 or 2-to-1 side slope on both sides, and you can see the solution failed. One thing I wanted to note was that when you get a no solution, a lot of these values they're not completed in the iterations, and so out on the values, if you don't want to rely on those when it says no solution. What I wanted to point out was that you see the D50. Even though this may not be a final iteration, it's indicating over class 3, and of course that's why it results in a no solution. But it was triggered by just changing the side slope here. And I wanted to note that because in ROC, HEC 15 does not recommend side slopes over 3-to-1 in steep slope conditions. We'll run the macro here, I thought. There we go. And use the 3-to-1. And you can see the D50 drop down to under class 3. You got a result, but as noted, you can still see it's the 3-to-1 side slopes versus the 6-to-1. Had a big impact on the D50. I'll do a quick pull-up of the hydraulic toolbox. Let's see. Okay. All right. There we go. That's HY8. Okay. I'll just add it to this file. Do new channel analysis for the same conditions. We've got 6-to-1 side slopes. Two-to-one bottom slope, 15% slope. You want to select the, what we're doing here, we're doing an analysis for the same conditions for use of TRM as an alternate. And so in order to do that, you got to utilize the vegetative analysis. The flow was 14 CFS. And you get the results. I don't really have time to go over those, but I did want to mention, you can see the depth here when you do the initial analysis is 0.647 on the depth. Now when you do the lining analysis, it will reiterate back to the channel analysis, and it will change the result. So you just need to know that. So we'll use that analysis, and we're in the riprap and rock, and what we're wanting is the vegetation. So we're going to go to the vegetation, and what you need to know about this is while we don't let's correct the input first. For Class C vegetation, it's going to be 8-inch as the standard for Class C. These are the default values for the condition of vegetation, good. Growth form of vegetation is mixed. You can see there are other options, and you should use those if it applies, but these are the default. The cover factor as a result of that is 0.75. Now, the soil parameters here, you want to leave the non-cohesive and just go with the default, because these only affect the effective soil shear and the permissive shear result, and therefore it's not relevant to what we're trying to achieve in getting a maximum shear stress on the channel bottom. They don't affect the result. The only thing that affects this result are these values here that were discussed. The resultant, I should note too, if you use the cohesive, you got a lot more data to input too as well. So we don't recommend that. Anyway, the result here is that maximum shear stress on the channel bottom was 4 pounds per square foot, and that puts us in the TRM class type 1, as was noted in the no, it's the wrong one. Is noted in the table. And that's pretty much the workaround for hydraulic toolbox to determine shear stress for grass. Now, the only problem, like I said, is it uses the HEC 15 method on vegetative roughness rather than the current KYTC manual. And there's one last thing I wanted to show. Surprise, I guess. As I mentioned in the other option, you can you can do a quick Manning's calc based on the, you want to find the depth for shear evaluation. You can put in the discharge and the bottom width, side slopes, and Manning's roughness estimate initially, and then a channel side slope, which was, or the channel slope, which was 15%. And you get a value, and it gives you a hydraulic radius. And then, but what you would do would be to iterate using the table. Let's see. And as you iterate, you would finally result, and narrow down to a result that you could use the end value. Get the required grass analysis done according to the drainage manual. Just by that simple method. So that's, I kind of just wanted to show that, and you would, we're over time, so I guess I'll stop. And so thank you very much.
All right, thanks, guys. Doug, can you put Mater back on real quick?
Sure.
I just wanted to reiterate at the beginning, someone asked about a copy of the slideshow. We will post the recording of this for future reference on the website, and we'll have a PDF of the slides for you guys as well. Mater, are you on there yet?
Yes, I am.
Can you tell everyone kind of where to find this information, the various software? Is it available through links on our drainage website, etc.?
Yes, you can get it. The links to this is on the drainage website for hydraulic toolbox, right, Doug? Yeah. Well, you can get the hydraulic toolbox from the FHWA website, and all you have to do is do a search on Google, and it'll come up very easily. I just did it at home last night. So, yes, hydraulic toolbox is easy, and of course H8, which everybody sounds like they have.
Yeah, and that's on the drainage website, as well as the spreadsheets. Okay.
Yes, the spreadsheets are there.
I also have a question, Mater, backing up. Can you see the questions that have been asked?
I am. Hold on, not yet. So, still looking.
It might be on your second screen.
I'm going to close this. Close this. Doug has opened up the world here, so I'm trying to close it down.
Yeah.
Okay, I do not see anything yet. So I've got the questions. Okay, hold on.
It's a long one, so I want you to read it.
Okay, let's see if I can make it where I can see the thing. Where do you download the software? I see that one.
We already took care of that, yeah.
Is there one below that or above it?
Above it.
I can't get. I see some words, but let me see if I can get to it. Wow, it is long, but I've got like a one. It's going to be hard for me to read it, but I'll try.
Okay.
Can you see? I can't. I'd be nice if I could see all of that. I can't see it. Maybe I can. Is that it?
Yeah, there we go.
Okay. All right. All right. It is. Is it always that with that freeboard? They're asking freeboard, right?
No, they're aged. That is level head water.
Right. Plus 1 foot.
Yeah, which is expected or offsite impacts.
Okay. Are you there, Kevin?
Oh yes, yes.
I think it is the first it is the allowable headwater plus the 1 foot. The 1 foot, yes. Okay, is the allowable headwater the height of the structure? Okay, let me see if I can.
It has nothing to do with the height of the structure. It has to do with the existing water surface elevation at the structure versus notice water surface elevation.
Yeah, I just need to, I guess, contemplate this. I want to make sure I'm understanding it. So maybe I just need to get back to this person with that.
Sure. Absolutely, we can do that. That's the only question that we haven't answered. If anybody has anything else real quick, send it. If not, obviously they can contact us or contact Doug and Mater directly through email or phone. We'll try to get every question answered that we can. Don't see any more coming through, so if you guys are okay. One last question. Is there an update to the drainage manual?
No, not right now. What is on the website is what is up to date.
Okay. Good deal. Well, I guess we'll go ahead. Oh, there's another one. Go Big Blue. Thanks, Mitch. All right. We'll go ahead and close this one down. I appreciate everybody for attending today, and hopefully it was a benefit. When we close this out, there'll be a poll. Please give us your feedback as usual. And again, thanks for attending.